Good afternoon, dear conference participants. My name is Pavel Trishin. I work as a lecturer at the National University Zaporizhian Polytechnic. This report is devoted to the regularities of oscillation in turning and milling. During machining under the action of the cutting force, the elastic system's tool parts goes out of equilibrium and oscillation of the system appear. To control and reduce vibration, enough research has been carried out, the main task of which was ensure surface quality and processing productivity. Many methods have been developed to suppress vibration. The following methods are most widely used: using high feed insert, using variable geometry tools, changing the cutting speed. Simulation of the general reaction of the assembly of the spindle and tool to the cutting process, using the stability lobe diagrams. It should be noted that the studies consider either the overall effects of vibration on the cutting process without division into types: forced, free, self-oscillation, or the influence of self-oscillation. The purpose of the study is determine of patterns of action of various types of vibration during turning and milling, to determine of priority types of vibration for various machining methods. Research tasks are: develop of research methodology, develop device for research, conduct experimental studies, analyze and results, and summarize. It's known that forced oscillations are formed during cutting. Forced oscillations are oscillations that occur under the action of external periodical forces. These oscillations are characterized by period and amplitude. Also, free oscillations are formed during cutting. Free oscillations are oscillations that occur in a system under the action of internal forces after the system has been taken out of equilibrium. Under the action of friction forces, free oscillations are damped. The amplitude of free oscillation depends on the initial conditions. Self-oscillation are most harmful during cutting. Self-oscillation and damped oscillation in dissipative dynamic system without external oscillatory influence. The self-oscillation amplitude does not depend on the initial conditions. In addition to the listed types of vibration, it is noted in the literature that accompanying free oscillation occur during cutting. Accompanying free oscillation of the technological system is oscillation when the tool cuts into the part. These oscillations have the characteristics of the free oscillation. To determine the regularity of action of vibration, a study was carried out during intermittent turning of cylindrical workpiece with a longitudinal groove. Turning provided a large cutting time. The turning frequency was provided by longitudinal groove. The research device was a cutter in the form of oscillator. The oscillation amplitude of the cutter was measured by displacement sensor. The design of the device used made it possible to adjust the dynamic characteristics of the cutter, registered its oscillation during cutting, and determine the cutting time. The samples were used from steel 45 and the cutter had VK8 hard alloy plate. Study of the regularities of the occurrence of vibration during milling were carried out on a special stand, which allows simulation the processing of parts. The device for measuring vibration was a oscillator, on which the sample was fixed. Up and parallel milling was carried out at axial depths of cut of 4 mm, a radial depth of 0.3 millimeters, a feet per tooth of 0.1 millimeters, and spindle speed of 120, 200 and 700 RPM. The design of the device used made it possible to control the dynamic characteristics of the sample, registered its vibration during the cutting process, and determine the cutting time. Samples were used from steel free and mill from high-speed steel with a diameter of 16 millimeters. The vibration recorded during the turning of the workpiece with the groove have characteristics features inherent in all types of vibration. At each revolution, the cutter hits the workpiece. As a result, forced oscillation occur. Forced oscillation occur under action of the cutting force, which presses the workpiece by the value of Bx. They are superposed by damped accompanying free oscillation of the technological system with a period of TAO. A wavy wake appears on the cutting surface, which is the source of undamped steady-state self-oscillation with a period TCO. Self-oscillation becomes steady after the transition period and before leaving contact with the workpiece. Then the workpiece moves in the absence of cutting, where a damped free oscillation of the cutter relative to the position of elastic equilibrium with a period TFO. Based on the results obtained, it can be started then regularity of action of vibration during cutting has the following sequence: forced oscillation superimposed on the accompanying free oscillation and self-oscillation. Free oscillation of the cutter relative to the position of elastic equilibrium after the end of cutting. Each type of oscillation has its own duration. Forced oscillation act during the entire cutting time, T-cut. The accompanying free oscillation act during the time TAO. After the attenuation and before the end of cutting, self-oscillation takes place during the time TSO. The free oscillation time of the cutter is determined by the idle time TIR from the end of cutting to the next cutting of the tool. Vibration during milling are characterized by low cutting time, which affects the types of vibration that occur. Then milling with a spindle speed of 120 RPM, only forced oscillation are active during the cutting time T-cut. Due to the peculiarities of change in the thickness of the cut layer during uphill milling, the indentation of the sample Bmax under the action of the cutting force is less than with the associated one. With increase in the spindle speed to 200 RPM, the cutting time decreases. In upcut milling, oscillation occur then are superposed on the forces ones. With accompanying free oscillation with period TFO, they act during the time TAO and disintegrate. After the cutter exits the cutting zone, free oscillation of the sample with a period of TAO act, which also decay. Increasing the initial cutting speed leads to increasing in the amplitude of accompanying free oscillation. Then the milling with a spindle speed of 700 RPM. These vibrations are superimposed on forced vibration, both in up-cut milling at the beginning of cutting and in crimp milling at the end of cutting. The occurrence of free oscillation and their attenuation during the end milling is associated with a change in thickness of the cut layer. Based on the results on the studies, the following conclusion were formulated. The regularities on the action of various types of oscillation during the cutting are determined. First, forced vibration act and accompanying free vibration on the technological system are superimposed on them. After their damping, adjustment occurs and stable self-oscillation occurs. The possibility of developing various types of oscillation depends on the cutting time. For example, then turning, then the cutting time is large, conditions arise for the action of all types of vibration. In the end milling, the cutting time limit does not allow stable self-oscillation to occur. The amplitude of accompanying free oscillation depends on the initial conditions. Therefore, as the cutting speed increases, it also increases. In further studies, it is planned to determine the effect of dynamic properties of the technology system and the amplitude of accompanying free oscillation of the cutting modes and tool geometry. We express our gratitude to organizers of conference for their help in preparing published material. We express our gratitude to Professor Zaloga, Professor Stupnitsky, Professor Tankanogий, Professor Permяков for research support. Thank you for your attention.